All right, I'm going to give a go at making just a really quick study guide video, just sort of a summary. One of the things I hope you noticed from the packet was that sort of everything is broken up into sort of tidy disciplines or contents, where it starts out where the beginning of the packet is all pressure related, sort of basic pressure, you know, definition, P equals F over A type things. And then you did, hydrostatic pressure, where you had a fluid above and you wanted to know what's the pressure at a depth, where it was rho GH. Maybe you had to incorporate atmospheric, maybe you didn't. Depends if it's an open or closed vessel. From there, you'll see that there's a lot of Pascal's principle questions where, remember, Pascal's says that in a closed vessel the pressure is equal. So P1 equals P2 is not the greatest solution to that, but when you expand it out, you get F1 over A1 equals F2 over A2, which allows you to see things like what's the force multiplication, that sort of the output force given, maybe you start with a small input area and a larger output area. This would be 2 and this would be 1 here. Big thing there is, pi r squared. Sounds simple, but if you double the diameter, what does that do to the area? It's 4 times the area, so you get 4 times the force. And there's other situations where that happens, which I'll talk about in a second, but in terms of continuity, where, real briefly, you have A1 V1 is A2 V2, area goes into that, so there's other questions related to, changing the area or changing the radius or the diameter. So from Pascal's, the next thing that we probably will see is Archimedes' principle. And the biggest thing that kids do wrong with Archimedes is that, they all understand or can say, yes, the buoyant force is equal to rho Vg, yay. But it's the weight of the fluid displaced. And I like to say it out loud because that forces you to think about what the rho is right here. And that rho is the rho of the fluid. So too many times when kids are doing things wrong, they say, a copper object is placed in water, blah, 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 and kids are plugging in, the rho of copper there, which is wrong. Okay? So make sure you're plugging in rho of the fluid. This is V displaced. Again, just give it a little bit of thought. If it's submerged, V displaced equals V of the object. If it's 50% submerged, it's half of V of the object. So just be smart about that. After that, I think that was the last thing we did in hydrostatics. So then we went to flow. Now again, taking a step back, if you're asked questions about pressure, if there's no flow, don't bother with Bernoulli's. If there is flow, then you're going to want to incorporate Bernoulli's, which is, rho G H1 plus 1/2 rho V1 squared equals the same thing rewritten here at a second location. Now, almost, I won't say 100% of the time, but most of the time, the fact that you have these two V's here means you're going to incorporate continuity at the same time. Because this is V1, and this is V2. So, the size of the pipe changes, the velocity changes, and you can incorporate that. So you're going to combine those two equations quite a bit. Remember this A1 V1, A2 V2, people are forgetting what the definition of that is. That's the volume flow rate. Volume flow rate. Again, this was derived in class, but it's volume over time. And we talked about, you have a pipe, maybe it changes, I don't know here. But the derivation where you had this slug of water traveling over time, it had to do with this cross-sectional area multiplied by the velocity of the fluid. It tells you how much that slug or that volume moves. And you can always check it with units. It's meter squared times meter per second. Gives you meters cubed per second. One of the questions, just an additional add-on, talked about the mass flow rate, which we really never talked about. But it's not a stretch to realize that the volume flow rate, if you multiply by rho v is just the mass. So it's mass over time. So that would give you a unit of kilograms per second, which is the mass flow rate. Again, not anything groundbreaking, just taking advantage of what you already know. Okay, I'm going to pause for 1 second and see if there's anything I missed. One thing I missed, Torricelli's theorem. I think this is how you spell it. It's basically just a simplified version of Bernoulli's that really only holds when you have some large tank of water. It doesn't have to be circular, but large tank of water with a small opening for water to come out or fluid to come out. And again, we derived it in class, but the idea is that because Bernoulli's is conservation of energy, it might be sort of a likely outcome to say that the potential energy related to the fluid at this height is probably going to turn into kinetic energy at this height. And it actually, you saw it based on the derivation in class, that the V out equals radical 2gh, where h is the height of the water above the opening. Okay, so that's Torricelli's theorem, but again, it's just Bernoulli's simplified. What are the simplifications, or what are the assumptions we make? That this is much bigger than this. So we could say if this is D and the opening is little d, it's much bigger than D, which sort of an outcome of that is that the V here approaches 0, the V at the top. So it's dropping in water level very quickly, or very slowly, excuse me. Pause. All right, some other things. Don't go past chapter 10-10. You don't have to do anything beyond that. Going backwards to Archimedes, some things that come into play there. Specific gravity is equal to the rho of, usually it's an object. So the density of some object compared to the density of water is usually what it's listed as. And that'll give you an indication of how much of the object is above or below the water line. So how much is submerged. This is equal to the percent submerged. So just be careful of some things, some tricky things. They'll tell you the percent above. So you have to subtract from 100% because you know the percent submerged based on this. There's some other tricky questions where one of the things you always have to realize is FB, it doesn't matter what the density of the object is. Density of the object is going to tell you if it sinks because that's its weight. But if you think about a free body diagram, mg, or like I said here, rho not v not g, tells you the weight. The buoyant force only depends on the water that's displaced. So this is displaced. So this could be any similar sized object is going to have the same buoyant force. This number will be the same. But if it's a really dense object, mg will be much bigger than FB and it'll sink. So that's if rho of the object is greater than rho of water. If rho of the object is less than rho of water, again, this number is the same, but m times g might be much smaller because the density of the object is so low, then it will float. Okay, so don't lose track of that. All right, so I'm assuming, I missed something within the 9 minutes here I've been talking. So if you have any other questions, shoot me an email and I'll try and answer them. But the biggest thing is take your time, draw a picture, especially for Archimedes when you're talking about buoyancy. Make sure you're very careful with your math. You guys are all really good at math, but some of you are butchering, how to find the area of a circle, which I won't name names, but you know who you are. So if you have any questions, let me know, but this is the end for now.